So, okay. As you know, today's lecture, which is my last lecture for this topic in this semester, is on numerical simulation of a forging process. Last week we talked about the forging process. I have introduced the different type of forging process and reviewed some analytical method on calculating the forging load. And for today, first we talk about the development procedure of forging process. It's a repetitive slide from the last lecture, and then we proceed on setting up a forging simulation, how we can set up a forging simulation. Of course, I will not give all the details on this topic, but the important parameters, the important factors, I will introduce the important factors in setting up a forging simulation. Then I talk about application of simulation in optimization of forging. I bring some example that how you can optimize or how you can improve the forging process using a simulation. And then we have a topic on prediction of grain size in forging. In 2-3 slide, I will talk about the prediction of grain size, because I think it's a little bit above the normal level of simulation and prediction, so you can become familiar with the prediction of metallurgical concept, not only the effective strain or the strain stress, but here we try to predict the grain size during the forging. And finally, I will explain about a few examples of simulation which are about the various type of forging process. So then you can understand that with the metal forming simulator or forging simulator, you can simulate almost all the forging process. So, okay, this is the slide we had last week, and today we focus on this part, especially on the modeling and preparing the simulation of forging process. Of course, the complete chain is like this, the complete flowchart is like this, but we do not talk about the manufacturing part. Last week I explained a little bit about that. So this slide shows that clearly, definitely, when you want to start the simulation, first you should design your master model or master gear here, because it's a gear part. The part is gear. You should design your part in a CAD/CAM, in a CAD software. So okay, this is the reality, and this is what we have designed based on the dimension we have in reality in a CAD software as a model. So this is, we can call it the master gear. It means that it's the part before machining and exactly after the final stage of forging. This is the shape we have. So first we design the shape of the master gear, and of course then according to the shape we have designed, then we can obtain first design of the die by the techniques, by the methods you have in any CAD software. You can make it negative and obtain the upper die and lower die. Of course, when we want to obtain the die, you should determine where is the separation line, and of course you should think about the how and where you should design the flash for the forging, and so on, and some other parameters. But the die cavity is obtained using this master gear model. And these steps could be different from one software, CAD software, to another software. It means which software, CATIA or SolidWorks, whatever you're using. Okay, after that, then you have a design for your dies. Then you can import the obtained geometry for dies into your metal forming simulator, as you can see here. But usually for forging, not all the time, but usually the part has axisymmetry. So you can simulate it in 2D. If you can simulate a simulation in 2D, it's better to follow this and do not simulate in 3D, except you have some excuse for that, you have some reason for that. Because in 2D, the number of mesh you can use is higher. I mean, the time, or I can say that the computation time is lower than the 3D. And from the point of view of accuracy, I can say that even the 2D, if you set up your simulation well, then you can obtain even accurate prediction. However, if you compare the result of a 2D and a 3D simulation for a similar case using a simulator, then you can find that the results are really comparable and almost similar. But as I said, to save the time and to make it simplify the model, then it's better to simulate in 2D if it's possible. For example, if it's an axisymmetric part like this we have here. Okay, so the first step is geometry, of course. In any simulation, is forging or any other forming process, metal forming process. First, you should import the geometry, and after that, what is important is the material of workpiece and the die material. For material for die and the die material or the workpiece, you have two different way. One is using the library of software. Usually software has library, so you can find your material, for example aluminium, this alloy, or steel, that alloy. Then you can import the properties of the material. These properties includes, of course, the mechanical properties in elastic part, in plastic part, thermal properties, some physical properties sometimes, and density, and so on. Okay, but the most important factor and property is the flow stress, of course, as you know well, because we are deforming the material, so flow stress is important. However, if your simulation is an elastoplastic simulation, then of course the elastic properties is also important, Okay, and you know that metal flow curves usually are depicted in this way for alloy and steel, and this is true stress, true strain here. But in some cases, when you go into the library of material, the curves are like this for different temperature and different strain. So you can see for different temperature and different strain. So conceptually, these curves are similar, but the way we are plotting is different, because here is the true stress and strain rate, as you can see. So I can say in this way that here we are expressing the true stress as a function of strain rate, here the true stress as a function of true strain. So because in this way the curves are a little bit simple compared to this true stress strain curve, then some software are modeling the material behavior using true stress strain rate. So it's usually they use the function like sigma equal to C epsilon strain rate to the power of m. So you can fit such an equation on this curve and obtain the C value and m value for different temperature and for different strain. And of course the softwares are capable of linear interpolation and obtain the value for the temperature in between or for the strain in between. Okay, and of course the same for the die. But you know that the material workpiece and the properties you give for the material workpiece, the material of workpiece is much more important. And then after that you should define the speed of deformation and of course the way you apply the load. We talked about the different mechanical or hydraulic press last week. So for selecting the die velocity, again you have two solutions. One is going to the library of software, and the software in the library you can find some standard type of the mechanical press or hydraulic press or other type of press. Then if you click, then you should give some parameters of that special kind of press you are using. For example, here a crank press is selected, so you have to give this diameter and the rod length, this one, and of course the strokes per minute. And even you can go to the advanced option and change some parameters which are defined by default for this kind of press. This is one way, and another way is to give the values in a tabular mode. It means that you can define the speed of the upper die. Usually this lower die is fixed usually, so the upper die you can give the speed from the beginning of the process in terms of time. Usually we use time at the t equal to 0 to t equal to, for example, a. This is the speed, and a to b, that is the speed, and you can define in this way. Or if the process is carried out under a constant speed, then you can give a constant speed for all the process from the beginning to the end. This is another important factor. So after giving the material and the speed of deformation, another important parameter is friction. Okay, usually we look into the friction as a simple problem and simple factor. Then we give just a constant value for friction, but in reality it's not like that. You know, we have different kind of model for friction. For example, we have the column friction, which this red plot shows the column friction and the relation between the tangential stress and normal stress when you are applying the Coulomb friction, and this one is the constant shear friction. But we may have a hybrid model like the blue one, which up to this level apply the Coulomb friction and then the constant shear friction. In the simple form, we give a value, just a value, for example, for this mu value, and then for m value for the constant shear. But even if you use the hybrid model, still it's not similar to what happens in reality, because the friction factor by itself is a function of the pressure you apply, the temperature, and the strain. Okay, for example, at the beginning, if you apply some lubricant on the surface of the die, for example, graphite, you can assume that the graphite layer on the die surface is almost homogeneous distributed. But when the deformation starts and some part of the die become in contact with the workpiece, then the lubricant layer, of course, will be in some parts thinner, some parts thicker, and in some parts even it can break. So when the lubricant condition changes, then the friction condition will not be same as before. That's why the temperature is important, strain, and the applied pressure is important to obtain a value for coefficient of friction. For example, in this case, the Coulomb friction is modeled as a function of these three main parameters. However, okay, in the simple form, you cannot give the coefficient of friction as a function of pressure, temperature, and strain, but you can give a constant value, or in the best situation, you can give a tabular form. It means that depending on the temperature, you can change the friction, or depending on the maybe pressure. But if you want to model it in this way, I think maybe depends on the software you're using for simulation, but maybe you need a subroutine to write a subroutine and make the for example, Coulomb coefficient of friction as a function of all these three. And of course, you should set your die setup. You should prepare your die setup, because when you import, for example, this shows the die and workpiece immediately after importing the file. So you can see that, for example, the upper die is not located at the correct place. Sometimes even the lower die is not. It depends on the way you design your parts in CAD software. But anyway, you need some positioning of the die and workpiece to make everything ready for start a simulation. And after setting up, of course, these are the main things. So the material, the geometry, and the friction, and setting up the die. These are four main parameters, but the parameters you have to define are not limited to these factors. For example, in forming control, then you have different parameters you can set here. For example, you can reset some properties. For example, effective strain. Usually at the first stage, at the beginning, we should reset it to 0, or not 0, but usually a very small value, because if you give it 0 in some software, usually it gives a numerical error. So it's very small value you can give here. And of course, if it depends on your process. If you have just a preheat at the beginning, then you should reset the temperature only at the first stage of the formation, for example to 1200. But if you have heating or furnace in between the stage, then you can reset this value for that stage to the appropriate temperature you have selected for your furnace. And so on. For example, for grain size, if you're predicting the grain size, then some values you should give. Not only the grain size, but some other parameters also should be given. That we talk about those parameters in detail in next slides. Okay, and finally, when you run, this is the output of the simulation in post-processor. And of course, you know that you after preparing appropriate simulation, then you should know how to extract the data, and that is another story. So that's another skill, I can say, that you should obtain if you want to work on simulation part, that how you can extract the data from the simulation to conclude something meaningful. Okay, and I forgot to talk about the meshing. Meshing and remeshing is very important, not only in forging simulation, but also in any forming simulation, as we talked about it before for drawing. So usually the software has a auto remeshing system that it starts to remesh, like here or on this part, when the distortion on the elements are so big. We talked about this before when we were talking about the theories on metal forming simulation. So meshing and remeshing is also important to obtain the geometrical accuracy, and of course the numerical accuracy are also influenced by the system of mesh you use. The best situation is to obtain the most accurate description with the minimum elements, of course, because if you know well that if you increase the number of elements, then the simulation time will increase. So you should choose the number of elements which gives a logical answer in your simulation. Okay, after this short introduction to the simulation of forging process, now in few slides I want to talk about the optimization of forging. And so how you can, you have a simulation, you can obtain some result. For example, you can detect some defect in some special part of this your final product, and then what after that? Of course, you should be able to give a solution for that. It means that just to find that you have such a defect in your final product is not enough, because usually when companies they know that they have such a defect. So the next question is that how we can remove defect and how we can solve the problem. Okay, then you should start to play with the parameters you have. For example, you should change the material. You should think about changing the die design, the process design, the type of press, and so on, the friction condition, and so on. So you can see the parameters influencing on the forging your quality, or forging the final forging product quality here. So under any of these factor, there are some other factors. Okay, to make it clear, I bring some example of optimization. This is an example of forging connecting rod in the engine, auto engine, and if you can see here an overlapping happens in the first design of die. In the initial design, exactly here, an overlapping happens. Overlapping means that the material on the surface falls on the surface again. So and then it goes to the depths of the part sometimes, and sometimes it remains on the surface. So then later you can find it as a crack, as a micro crack in the product. And this animation is showing how this problem is removed. So if you compare the die design here with the die design here, you can find some differences. For example, here, and okay, compare with this one, which is flat, and no overlapping happens here. So the problem is solved and the defect is removed. But of course, with not only with a single try, not only with trying a single simulation, some simulation are used, and then finally they could solve the problem, and then you can suggest to the manufacturer the new design. The next example is the application of the forging simulation for simulating a fully coupled analysis of die material in terms of deformation and heat transfer. Okay, if you look into the problem of forging, simply you have workpiece, upper die and lower die, but it's not like this. Usually you have much more parts beside, for example, a supporting ring and some other parts. So if you want to consider all the parts here, the workpiece, upper die, maybe upper die would be formed from different parts, and lower dies also, then you can give all this detail in your simulation in this way. And of course, if you want to simulate such a simulation, a full coupled simulation, coupled means the die and the workpiece both are simulated. You will have the prediction. For example, here you can see you have the prediction of temperature in workpiece and the dies, and accordingly you can predict the residual stress and other parameters. And using this kind of simulation, even you can study the die life, the die wear, and some other parameters which are related to dies. Okay, so if just we look into the material and workpiece using simulation like this, then yeah, you can study the metal flow line and talk about the properties and the accuracy and the soundness of the workpiece you produce. But if you want to simulate a coupled simulation, investigating the workpiece and the dies, then the story is different, but it is possible to simulate. This is a 3D simulation, a coupled analysis for a 3D simulation. The previous slide was the 2D. This is the 3D, but yeah, the approach is same, just the dimension is not 2D, but it's 3D. And of course, in this case, if you want to simulate, in this case, or in 2D or 3D, both, if you want to simulate a coupled analysis, coupled means coupled heat transfer and coupled deformation or mechanical properties. So at least you should have a thermoelastoplastic model, because you have some dimensional change due to the temperature change, and of course some deformation, elastic deformation in die. So it depends on the accuracy of your simulation you need, but in some special cases, of course you should give the elastic properties of the dies. In some cases, you can assume the die as a rigid die. It depends on what you want in simulation, of course. Okay, and this is another example of a coupled analysis of deformation of die and material. So you can see that the die is not a simple die, but there are different parts, and then if you give the data for the model, even you can predict the wear in die, because you know how much is the temperature, you know how much is the pressure on the die, and based on the value of this state variables, and if you define a wear model, then you can predict how much would be the wear in your die. In this simulation, for example, it's showing a high risk of wear here. Okay. This is another example of optimization, but it's the dimensional optimization, not in terms of quality. Of course, it's both. I will explain. This is the initial try, or the initial design, but then and this is the simulation of initial design, of course, and the part after the forging, the weight of the part after the forging is 1.1 kilogram here, but then the design is improved by the simulation, using a simulation. For example, if you compare this one to this one, so you can find that here is removed here, and some small changes you can find, and then the weight of the product after forging is reduced to like 0.9 kilogram, almost 200 grams reduced. And maybe you think that 200 grams is not too much, but it is, because as I said before, forging is the mass production. We're talking about the million parts or above. So even a small reduction of weight would be helpful for the manufacturer. And again, from this step to this, some small modification applied, and from second design to the third design, not only the weight is decreased to 800 kilogram almost, to 800 gram almost, but the metal flow lines shows that the quality of the product is improved. Okay, why? Because in the case that you are predicting the metal flow lines, this sharp nose, it's not good. This sharp nose would be source of defects, like cracks and other defects. And the more the higher the homogeneity of the material is, the better. So if you compare the metal flow line in the second design with the last design, you can find that, okay, these parts will be removed in machining after. So for example, this area which we have a compact metal flow line will be removed. But if you look into the part which remains after machining, then and compare with this one, you can see that more homogeneous distribution of metal flow line you have in this design. So this is another story of optimization in forging, or another example I can say. And again here, if you compare this non-optimized design with this optimized design, of course the size is not different, but the flow lines is really different. You can see here again you have this sharp nose and a kind of turbulence in the metal flow, but here it's not like that, and you have a homogeneous distribution of metal flow line, which leads to a better mechanical properties finally. And yeah, this is another example of improving the or obtaining the optimal design in terms of metal flow lines in another example. So, and I think this is the last example for optimization of a process design. Okay, as you can see, it's a two-stage forging process, and we have an objective in the optimization, the maximum load of finisher. We want to reduce the maximum load in finisher. How? By changing the die design. So in blocker, we have 2 points here, point 1 and 2, and the radius of point 1 and 2. We want to determine how much could be the radius of these corners and how it affects the final load at finisher stage. So okay, you should have a design of experiment, of course. Okay, assume that you do not have a simulation tool, then you should design different dies with different value of corner, radius of corner here, and then try it in practice. Of course, we do not do this because we have the simulator. Then in simulation, one approach is designing different dies with different radius at the corners and run the simulation and obtain the load at final load at finisher. But then you will have a matrix because you have two parameters which are changing, the corner at the point 1 and the corner at point 2. So, and in this range you should try some values, then finally maybe you may run 50 simulations, for example, and then you should choose the minimum value of the forging load at the finisher. But still you cannot be sure that that's the exact minimum, because maybe the minimum would be a little bit like nearby that value, but not exactly that one. So sometimes we can use the optimization schemes. Most of the simulator, or some of the simulator, it's better to say some of the simulator, they have a optimization scheme by themselves, it's included in the package. So what is the optimization scheme? Optimization scheme are the mathematical method which they suggest some value to reduce the try and errors to obtain the minimum based on the logic they have. So if you use a optimization scheme, then you can obtain the minimum value as it's used here, for example, with less number of iterations, for example 20 instead of 50. I can say this is a complete example of optimization. In this case it's a geometrical optimization, but it could be optimization in any field, for example the friction factor, whatever. And even if the software has not the optimization scheme, then you can link your simulator with other software which are they are only the optimization motors, and they have the different optimization schemes. For example, HyperStudy, HyperMesh is one of the examples. So you can pair any software or any simulator with that optimization engine, optimization scheme, and then you can run. And usually the runs in this case, when you are using the optimization schemes, the run are automatically started. So if you set your optimization scheme, and then for example you can come back after 2 days or after 1 day and just see the result, how much is the minimum, and how you can obtain the minimum load at the finisher stage. So no need to sit and run the simulations one by one. Depends on the capacity of your computer, of course. But if you go through the first approach, like the design of experiment just manually, not using the optimization scheme, then you should run the simulations, of course, manually. So there are more than a single advantage if you use optimization schemes. Faster and easier way to obtain the optimum condition. Okay, and this slide shows we have a defect. We have not a defect in the forging, but it's a phenomenon. We name it air pocketing. This air pocketing can happen in cold forging or hot forging, both. You can see here this air pocketing. The air is trapped between the workpiece and the die, and it may lead to a defect in the workpiece, or here you can see. But changing the design, you can remove such a defect, as it is removed by changing the design. Okay, you cannot any change in the die here, but maybe some other parameters or some other parts of the die is modified, or even the initial shape of the work, the shape of the initial workpiece is changed to remove such a defect. Okay. And the next topic is prediction of grain size in forging. Till now, when we talked about the simulation, in rolling, in drawing, forging, we just predicted the state variables, just stress, strain, temperature. But okay, we can predict these parameters, but the simulation is not just limited to these parameters. Then you can go deeper, and you can predict some metallurgical properties, microstructural properties, and so on. Of course, using the predicted state variables. Okay, now we want to talk about this. Generally, three main parameters you have. If in the case of when you have metallurgical phenomena like dynamic crystallization, static crystallization, or recovery, then the temperature, the grain size evolution, the deformation. The deformation includes the strain and strain rate by itself, and then temperature. These influencing factor determines that which phenomena will happen or which phenomena will not happen. Of course, the material property is important. We talk about it here. But basically, temperature, strain, and strain rates. So if you look into these equations, then you can find that these are the main parameters. And of course, you may have different approach to predict the, for example, microstructural evolution or the grain size. You can use a simple phenomenological model. This is a phenomenological model, but you can use the other, like the multi-scale modeling, which Mr. Qayyum will talk about it, I think, in a lecture in detail, or a neural network, or other approaches. What our example today is about the phenomenological model. This equation is a set of equations that you can predict the grain size after dynamic recrystallization. It consists of two main parts. This equation predicts the grain size, and this equation predicts or calculates the fraction of recrystallization. And so why these two should be predicted? Because the average grain size is not only dependent on the predicted grain size, but also depends on the fraction of recrystallization. Okay, imagine that 50% of the microstructure is recrystallized and 50% not. So the 50% of microstructure, the grain size has the initial grain size, and the second half, the size after recrystallization. So you should make kind of average to predict the overall or the average grain size. So you need these two, x drx, which is the fraction of recrystallization, dynamic recrystallization, and ddrx, which is the grain size. Okay, for calculating this x drx, this is based on the famous Avrami equation. We know the Avrami equation, and to obtain, to model and to calculate the fraction of recrystallization, here you can see that you need some parameters which are the material constant like the beta and the k here, and some other parameters like the epsilon 0.5 or epsilon peak here. So what is epsilon 0.5 is the strain at the 50% recrystallization. So when this is the peak strain, epsilon peak, this is the steady strain, and when it's the stress is in the middle, for example 50%, between exactly in middle of the peak and steady, then you can read the value of the strain as the strain 0.5 or 50% strain. So this value for epsilon 0.5 and epsilon peak epsilon can come directly from the flow curves, or even you can model these values using this kind of equation or any other kind of these are just example. There are many other models, mathematical models, to model these parameters. This is just a set of equation, as I bring it as an example here. So of course some other parameters here for the grain size of you need some other parameters. This H reflects the effect of initial grain size, N is the power of strain, M is the power of strain rate, and activation energy for recrystallization, and so on. So you need I think 5 or 6 parameters you should give to the simulation. Then your simulation will be able to calculate the grain size. Okay, finding these parameters are a different story, because there is an approach in which normally is used. We're using the Glebel test. You should perform the hot compression test with the Glebel test at different temperature and different strain rate, and then when you extract the data, then you can obtain these parameters. Of course, you should measure the grain size on your samples also, and then obtain these parameters. It's a time-consuming procedure. However, there are some other practical methods. For example, I have suggested a practical method in my PhD thesis. If you are interested, you can search and find the related papers. Okay, finally, if you have the parameters for the material model, for the model for on the predicting the grain size, like this equation, I can say for this example we do not need this value at all, because it's a hot forging, and usually if the temperature is high enough, that is usually, and the microstructure would be or will be 100% recrystallized after the forging, hot forging. So this value will be 100 or 1. So no need to input these values, then you can directly calculate the DDRX. However, even for calculating the DDRX, you need some parameters, as I said, A, H, N, M, Q. These are the suggested set for this material. Okay, I cannot remember what is it's a type of steel, but I don't know which steel. Anyway, if you give this, and then the simulator can predict the grain size distribution as it is depicted here in this figure. And okay, the black one are the measured value, the red one are the predicted, and the shows that the prediction are in good agreement with the experiment. And this is another example of prediction of grain size at the different sample point in a 3-stage forging process. And okay, the essence of this slides is that just to show that the simulation is not only limited to the strain rate, temperature, and so on. if you you can develop your subroutine based on these state variables to calculate whatever you want at the skill level. And sometimes you can you can find these options in the user interface of the software package. Then just you give these parameters and calculate. For example, the grain size, the die wear, or whatever. And the last part of the lecture for today is the simulation of various type of forging process. Okay, here you can see many examples of simulation of the products, and if you check in detail you can see the most of them are forging, but however the drawing and maybe the rolling are included. And in this part I want to show you that how powerful is the simulation and how flexible is the simulation or the simulator to predict the different type of metal forming process. As the first example, this animation is shows a open die hammer forging. We talked about the open die forging last week. This is the reality or the real process, not exactly this, but a similar process. And then, if you remember, I told you that the open die forging is for large object. As you can see, it's a very large, low pressure turbine rotor. 25 ton is the weight, so it's so big. And so if the objects are so large and if the number of parts produced is small, for example, you want to produce 2 or 3 or 5, it's not a mass production, then it's not logic to make such a big die for just producing 1 or 2 or 5. Then you should find a solution. That solution is open die forging in this case, because in this way you can deform the initial workpiece, you can increase the mechanical properties because you are applying the work. And of course you cannot obtain the final shape or even the shape near or close to the final shape, but its solution, economical solution, which can which can produce what you want. Not exactly, but then you should have apply some machining in the manufacturing, some machining to obtain the final parts. But of course the mechanical properties is much more better than the case that you just, for example, do the casting and then machining. So here you have a big casting part, and then after casting, open die forging, and then finally machining. On the other side here we have a closed die forging. The closed die forging, it's more accurate and more close to the final shape you want, and the pressure is higher. As we said before, the components are smaller in the case of open die closed die forging, and but of course it's expensive compared to the open die forging, because in open die forging you do not have to make the die, and the process is much more simple. So you can see that we can simulate the open die forging, the closed die forging. This is an example of high speed radial forging. This animation shows that it's a high speed radial forging. You have 2 or 4 dies here, and the workpiece has the axle moving and rotation at the same time, and the deformation is applied. And this figure, it should compare the experiment and prediction, and you can see the metal flow line here. If you look into the figure and if you compare, then you can conclude that the prediction in the term of metal flow line is almost similar with the experiment. This slide is about another process, swaging or recursive axial forming. We talked about the swaging before in drawing. If you remember, at the beginning of drawing, you should be able to pass the material from the die. So swaging was required. And here the process is similar to swaging, but not as simple as swaging. Some details, you can see some details are reflected to the workpiece using the die, and yeah, you can see that the simulation is able to simulate such a complex and complicated process. This is an example of hot plate forging. So in experiment, you can see a kind of necking at the corner here, and in the simulation result also you can see that it is predicted. Such a defect is predicted here in the simulation. So maybe by changing the radius of corner here, or by changing the frictional condition, we can solve this problem and remove such a necking here. This is an example of self-riveting simulation. I think you know what is the riveting process. It's a joining method, I can say, but the material is forged. So I bring it here in under the category of forging. However, the riveting process is a joining process, like the welding, but it's a mechanical joining, not. So what you can see here, that you are able to simulate even if you have different bodies. So you have two sheets here, which we are trying to join them, and a rivet here. So three different bodies here, but you can simulate even such a process. But the important thing here in such a kind of process, such a kind of simulation, is the contact surfaces. The contact surfaces and the scheme used for the contact surfaces should be perfect to be able to simulate such a process. And this is another example of rotary forging simulation. So here there is no animation, but I can explain that you have this upper die. This die is rotating, but not around the axis of material, but around this axis, which has the angle of alpha with respect to the axis of material. So by rotation, this kind of deformation is applied at the top of the workpiece. This is radial forging, radial ring forging. So you can see the thickness of ring is decreasing. It's a kind of open die forging. So in this case, if you have a big initial workpiece and you want to increase the diameter and decrease the thickness in this way, you can apply such a process, and of course you can simulate it using the forging simulator. This is roll forging. It's a combination of forging and rolling, so but you can see at different stages you can produce such a part, such a product, and finally this is an example of powder forging. Usually we assume that the material is the continuum, but you know that in the powder metallurgy you can even forge the powder. In that case, in the case of continuum material, we assume that the volume is constant, and this assumption is almost correct. But in the case of powder forging or powder metallurgy, the volume is not constant, but the volume decreases when you apply the pressure, as you can see here. So even you can predict such a behavior in the powder forging, and you can see the volume is changing when you apply the force. Of course, in the case of continuum material, in the case of not the powder, sometimes you see volume change, not too big, small, but that volume change is, if you check in the software, sometimes you see volume change, a small volume change, a small increasement or a small reduction of volume, but it's not, it's just a numerical change, not in reality we do not have, but in simulation we have, and that is because of the remeshing. When remeshing happens, a small volume change is unavoidable. So it happens in the case of remeshing. But that is different from this kind of volume change we have in powder forging. So I think this is the last example of the simulation. Today we talked about the forging simulation and the fundamental factors affecting the forging simulation, and then predicting the metallurgical parameters like the grain size using the simulator, and finally I introduced some various type of forging process that you can simulate using a metal forming simulator. Okay, as today is my last lecture on this topic, and other lecture will be given by Mr. Gayoum. So if you have any question regarding the today lecture or the previous lectures, I'm ready to hear and answer. That we have enough time to answer your questions. Okay, so if there is not any question, then I close the today's lecture, and of course the final exam will be an online exam, and the more detail will be Mr. Gayoum will give you the more detail that how would be the exam, because he will have four lectures for you later in 2 weeks. Okay, thank you, and okay, thank you and bye. And I think there is no question, so I close today's lecture, and see you in final exam.